In this lab, we want to apply the idea of a spatial joint. In manufacturing or in assembly, we often have a part that moves by gravity through inspection or through sorting or through packaging. And so let's watch this bearing fall along this track. So we might be interested in that motion of the object. Stop the video. Attempt to duplicate this design and the motion simulation using dimensions of your choosing. To set this up, I'm going to start a new metric part file. I'll select standard millimeter IPT, and I'm going to go to the right side on the view cube, and I'll start a new sketch on the YZ plane, and I'll draw a line over horizontally back to the origin and then down vertically. I'm going to change these two lines to constructions, and I'm going to change this line to center line, and I'll make these two lines equal length. I will then dimension from this point up to the center line a distance of 200. I'll then draw a line from the end of this line to the midpoint of that line and finish sketch. Let me go ahead and save this, and I'm going to create a new folder, call it loop to loop, and I'm going to put this file inside of there, and I'll call it track. I will then do a coil, and because we have an open loop, it automatically defaults to a surface body, which is what I want. I'm going to flip the axis direction so that it's following along this center line, and I'll do revolution in height. I'll do 1.2 revolutions in 50 millimeters. We'll say okay to that. Alright, then I'm going to create a plane perpendicular to this curve, and so I'll do a plane, and I'll select that curve, and I'll select this point, and again the right side is looking here. Now if I turn on that YZ plane and I look at this from the front view, notice that this plane that we just created doesn't match the YZ plane. So I see beginners a lot of times will start a new sketch on this plane, but it's not perpendicular to this path. And if we had just done this as a solid coil, the same situation, they would start on this plane, but that plane, the YZ plane, isn't perpendicular to this helix. So we needed to create this plane perpendicular to that helix. I'll turn off the visibility of the YZ plane. I'll do a new sketch on this plane, and then I'm going to draw a circle, and I need to project that endpoint first. So I'll project this point, then I'll draw a circle, and I'm going to make the circle a diameter of 24.2. I'll draw a rectangle, and I'll initially put it out here in space. Then I'll do coincident the midpoint of this horizontal line to the origin. I will dimension this height as 20, and I'll dimension this width as 240. Let's make that 40. Okay, then I'm going to sweep this portion of the profile along here. This 24.2, we're going to make a sphere to go in the track, and the sphere is going to be 24 millimeters, so I've allowed 0.2 millimeters of clearance. And so we'll do the sweep. I'll select this as my profile, and this is my path. We'll say okay to that. Turn off the visibility of the surface body, and turn off the visibility of the work plane. Okay, then I'm going to thicken this face right here, and I'm going to go a distance of 300 millimeters, and it tells me that it couldn't do that, and it says it doesn't produce a meaningful result. I'll edit that, turn off this automatic blending, and then it will work. I'll do thicken again. I'm going to thicken this face, and this time I'll go a distance of 200. I'm then going to start a new sketch on this face. So I'll click on that face and I'll do a new sketch, and I will project geometry this line on the bottom of the part, and I'll also project one of these corners, project this corner right there. And I will draw a rectangle, and I'm going to put that rectangle somewhere out here in space initially, and then I'm going to put the midpoint of this line somewhere onto this line. So I'll do coincident, I'll select the midpoint of this line, I'll select this line. I'm going to change this line to a center line, and I will dimension the diametral dimension from here over to here, and I'll do that as 120. I will dimension the height of this as 64. And I'm going to do coincident between this line and this point. So I'll do coincident, select that line, select this projected point. Everything turns color, it's fully defined, but I want to put more geometry in here. So let's draw a circle from this point. Let's trim off the arc, and then I'll dimension the radius of this as 42. I'll then draw a line from here down to here, and I'll dimension the diametral dimension from here to the center line, that distance as 24.2. I'll finish this sketch, and then I'll do revolve, and I'm going to revolve this area around the axis, and then I'm going to do revolve again, turn on the visibility of that previous sketch, and I'll do revolve, and I'm going to select inside this arc, I'll revolve that, and I'm going to put it on cut away that inside, and then I'll make the previous sketch visible again, and I'll do extrude, and I'll select inside this profile, and I might want to select both sides of this just to be sure, and I'll select cut, and I'm going to go to this face. I'll turn off the visibility of those two sketches. I will put a fillet on this edge and on this edge 2 millimeters. Say okay to that. Now I may want to put some colors on here. If I come up here to the library of appearances, I might want to put this on the Autodesk appearance library, which gives us more appearances than the Inventor material library. And so now when I click on this, it's now on the Autodesk appearance library, and I can go down and select whatever colors or materials that I want. Maybe I'll do a wild cherry. Now if you want to adjust the colors on here, if I click on adjust, and I will pick up that texture, that appearance with the eyedropper, and then if I want to scale that, I can drag this up or down to scale it as appropriate. And if I want to rotate this, I can rotate it. And then you can do that with each of the faces to get the appearance that you are after. Save this again. Then I'll start a new metric part file. I will create a new sketch on the XY plane. I'll draw a circle at the origin. I'll dimension this circle as 24.2. Or actually we want this to be 24, so we'll have a 0.2 clearance with the track. So let's do this as 24. I'll draw a line across here, and I'm going to put it out here initially, and I want that to be vertical, and then I'll do coincident the midpoint of this line to the origin, trim away half of this, and then I'll do revolve about this vertical line. And I want to apply a material. Now there's a difference between applying appearances and applying materials. If I go to the material, this will actually put the physical properties of the material that I select. In this case I'm going to select a stainless steel. Now if you don't apply this material, it would have the same mass as water by default. And I might then want to change the color of this to something else. I'll go back to the Inventor material library, and I'm going to change this to chrome. You can use whatever color that you like. Actually, I think I'll use yellow. One thing you might want to do, particularly if you use chrome or some highly reflective color or appearance, is go to Tools, Application Options. On the Colors tab where it says Reflection Environment, you may want to change to one of the other reflection environments, particularly if you get a motorcycle in the parking lot and you don't want that reflection in your part. I'll save this. I'm going to call it yellow bearing. Whatever name you like. And so that completes our two parts. Actually, I want to do one more thing on this. I want to put a point at the center of this. I'll click on this face and do a new sketch, and I'm going to project geometry this point and this point. I'll draw a line across here and put a point at the midpoint of that line. I'll finish sketch, and then I'm going to put a work point at that midpoint. I'll turn off the visibility of the sketch. I'll turn off the visibility of the work point, save the file, and then we can go to the next step of creating the assembly. I will then do a new metric assembly, so I'll select the standard millimeter IAM, and I'll go ahead and save this, and I'm going to call this loop deloop. I will place, and I'm going to place the track. I'll right click, place grounded at origin. Now you may not want it to come in looking like that. Notice the bottom is oriented here. I'm going to rotate this around, and I'll click on this corner of the view cube, and then I'll right click and I'll say set the current home position at that fixed distance. So now whenever I open this file or I click on home, it will go to that position. I'll then do place, and I'll place the bearing. I'm then going to put this bearing at a home position to start right up there. So I'm going to expand the origin on these, and actually we put a point here, so I need to go to the modeling view of the part so that I can get that point. So here's that point that we put up here at the track, so we don't have to have it visible in order to select. I'll do constrain. I'm going to constrain that point to the center point of the ball. Go back to the assembly browser. Now I want this ball to be able to move. Right now it's constrained there, and so I'm going to rename that constraint that I just put in here, and I like to name this home position. And as a reminder, you might put suppress this. And so anytime I need to get that ball back to that home position, I can unsuppress it. So I'm going to go ahead and suppress it. And so now that ball can move anywhere. If I want to get back to the home position, I go back and unsuppress it. And then so that it can move, I'll suppress that constraint. I'll then go to dynamic simulation. And we notice that both of those parts are in the grounded group. So we need for this sphere to have 6 degrees of freedom. So we need to put a spatial joint on there. So I'll do spatial. And it asks me to select the first component. I'll select the first component, and for I might want to set the origin now up there where that point is. So I'll go to the modeling tab, and I'll select the point up here on this part as the home position for component 1, and then for component 2 I will select the center point over here from the yellow bearing, and then that selects these as the origin, the same location, and I'll say so that it doesn't have to calculate that center of that sphere. So now if I go back to dynamic simulation, we see that we have the spatial joint on here, and the bearing has been moved into the mobile groups out of the grounded group. But if I play it right now, nothing happens because we haven't defined any forces acting on that bearing. So we need to put gravity. So I will go to the external loads, I'll right click, define gravity, and I want it perpendicular to this face. And then if I play this, it falls, but it goes right through component 1, so we need to define 3D contact. I'll go to 3D contact, and for component number 1, and again I prefer to use the points that we put into the component, so I'm going to select this work point in component 1, and then I'm going to select the center point in component 2, and we'll say OK to that. So now we've established our 3D contact. I will play it, and we'll see that it starts to go down the track. It's doing the calculations of velocity, acceleration, so forth. So it takes longer to analyze the motion of 1 second than real time. I play it a little bit longer so that it can go down through the hole. So let's do 1.5 seconds. We can increase or decrease the number of calculations that are occurring. And let's go ahead and open up this output grapher. And with the output grapher, perhaps I want to graph the velocity or the acceleration of the ball. Now there's 6 degrees of freedom, so we can graph along the rotational or translational degrees of freedom. I'll do to the position, and I'll do one of the positions. Now we would have to analyze which one of these goes along with which particular degree of freedom. If we go to the spatial joint and we go to properties, so we see that 6 is the translational degree of freedom, and we'd have to find which one that is on the sphere and so forth. So here are the various degrees of freedom, but graphing those positions. So this is why it takes a long time to calculate the motion, because it is keeping track of all of these physical dynamics that are occurring with the motion. Let's put a trace on this ball. So I'm going to do trace, and for the origin I will select the center point of the bearing, and we could also have it keep track of or create output file of that trajectory. I'll just play the visual trace and we'll play this again. So this time it's tracing the center point of that ball, of that sphere, as it moves. Now after we have played this once, it will play back much faster. So I'll just do rewind. Don't go all the way back to construction, just do rewind, and then I will play this again. Now it still isn't 1-to-1, the calculation versus the display, but it does play back faster. Later on we'll see how to do it at 1-to-1. So that was an application of the spatial joint.